Okay, to start with, in control system, the simplest form of control is measuring the output and working on the variable that could be manipulated. So, what is called as a feedback control system. And there are some variables we don't have any measurement. What is called as some disturbance variables. So, we don't know in what way they are going to affect. Still, we are able to control the system based on the measurement of the output and taking some action. Using this simplest form of controller like PID controller. And in that we discussed about the role of proportional action. With the proportional action, we had seen that we could not eliminate offset. Otherwise, there is a persistent offset. To eliminate that, we tried the other mode of controller, what is called as integral action. With integral action, the overall order of the system is getting increased. Say, for example, the first order system is turning to a second order system. But we know this second order system is also introducing what is called as cyclic behavior. Of course, that can also be eliminated provided if you set value of this damping factor greater than 1. But more often with controller system, we'll be having this cyclic behavior. With eye control, we could eliminate this offset. Say, if you change the set point to a value of 1, the overall output also should reach a value of 1. There is an expectation. There is a meaning of changing the set point. What is called as we are always how fast, how good the system is cope up with the tracking. Always how the system is capable of meeting the tracking the set point. What is called a set point tracking or servo problem. So said you will change the set point to 1, outputs also should equal to the value of 1. With P control, it is not reaching to that final value of 1 or reaching to the value of the set point. Instead, it is below the set point value. The difference is called as offset. To eliminate offset, this integral action is good, but integral action is leading to oscillations. So these are all the aspects we covered in the last classes. The next aspect is what is called as a derivative action. So derivative action, you know, the equation of the controller equation we had, no? Yeah, I don't have that equation here. Yeah, you know, this derivative controller is Kc into tau ds, no? That is the response of the GC. For the proportional control is simply Kc. For integral controller, it is Kc by tau is. And for derivative controller, it is Kc by Kc into tau ds. So let us see that. So okay, this already we discussed. This offset, to eliminate offset, we had introduced this integral action. Because of that, the overall order got increased, but offset is offset we could eliminate. And derivative action, this is the derivative action. Quick I will try to give a demonstration with our Simulink, and we have to go to the next topic, which is about stability. So for the coming test, which is coming on this Saturday, are starting on Thursday, no? So before Thursday, we have one more class on Wednesday. On Wednesday, we'll discuss about the simplest form of stability analysis, what is called as route stability. That's the class. For that, we will establish basis in this today's class. So we'll quickly see about the action by derivative action, the derivative mode of the controller. So the controller output depends on the derivative of the error. This error is E of t, and derivative of the error is dE by dt. So E is a function of time there. So E of t is there. Okay. And the transfer function is simply given as Kc into tau ds. That is, for the derivative, it is S into E of s, and C of s by E of s is called as a Gc of s, or simply Gc. Class follow pandringalappa? Okay. And okay, we can make this as like the previous derivations. Previous derivation enna pannom? Say this is your closed loop system. And for simplicity, we are taking this measurement to have a transfer function of 1 and final control element to have a transfer function of 1. And GP is also assumed to be a first order system. Otherwise, we need some reference. No? And GD, okay, we take it as this disturbance is 0. Otherwise, how far the system is capable of coping with the set point change, or what is called a set point tracking for the set points, set point tracking or servo problem. The same is also applicable for for this disturbance problem, what is called as a load change or regulator problem. You can also erase in place of this the equation. Which equation? So in place of this group, otherwise you can simply take this set point change is equal to 0. Otherwise we don't change the set point, and we can consider for the changes in the disturbance. So அதுக்கும் derivation பண்ணி you can obtain the final relation. Say normally we will change the set point to a value of 1 and we will see the response. The output should also equal to the value of the set point. Whereas in the case of this disturbance problem, what is called as regulator problem, for say if you change the disturbance to a value of 1, the output should still be at the value of its initial steady state. Otherwise, for any changes in the disturbance, output should not change. That is the expectation. Say the disturbance changes now. What is the meaning of? So there is some regular flow, and suddenly the flow is changed by some inadvertent or by some means. So we should still get a response with a closed loop, otherwise the output should not change. That is the expectation. Otherwise, for any changes in DS, the OS should not change. Otherwise, the expected value of OS should be equal to 0. Otherwise, with control, the red color should again fall to the value of the y-axis. Otherwise, this is the horizontal line, then it should be falling in the value of y equal to 0. It will increase again. It will match with the value of y equal to 0. We'll expect. Otherwise, in that case, offset in comparison with the value of 0, how the output is. Otherwise, here we are comparing with the value of 1. 1 minus this output is called as offset. In that case, we'll be having simply 0. Comparing with 0, 0 minus output is called as offset. Maybe அதே ஒரு சின்ன இதுல ஒரு சிமிலிங் கேஸ்ல we'll see. Okay, today's topic is about derivative action. So derivative action la enna pannom, loop. Okay, the numerator enna paarkom, the numerator consists of GC, GP and GM, and here we have 1 plus we won't have GM in the numerator. So I will again go back to the transfer function. So the transfer function of the closed loop, this you can derive GP, GC, GP, what is GF? Final control element, GC. So elements in the forward direction divided by all the elements in the loop. So in the loop, in addition to the GP, GF, GC, we also have GM. And for simplicity, we are taking GF to be 1, GM to be 1. So we have, and we have studied about the various GC. What is GC equal to KC for proportional controller, or with the integrated controller, KC by tau is, and for for D controller it is KC into tau ds. So that is what is I explained here. Yeah. So your GC is equal to KC into tau ds. We have GP, which is KP by tau ps plus 1. And you can expand this. And this still again appearing similar to our first order system, except for the S term in the numerator. Of course, what is the role of S in the numerator? That we'll see in the coming thing. In the pole 0 response, this in the left hand side, it is still a first order derivative. Right hand side also we have a derivative. If you write in terms of a differential equation, this output form, this is output form. No? This denominator is the output. So output is having S in the denominator. So say S in the S term, which is derivative term. Likewise, input is also having a derivative. So still it is a first order system. So otherwise, order of the system doesn't change. That is, with D control, order of the system doesn't change. Whereas the response, how fast it is responding, that we can say from the value of the tau, group of the tau. So here the tau is changing to, not tau, referring to tau p. Tau p is changing to tau p plus kp kc tau d. Otherwise, the your time constant is getting increasing. Time constant increase means the response will be slower. Otherwise, with derivative action, derivative mode, we'll see the response becomes slower. Okay, there is a final result with this derivative mode of the controller. So order of the system remains doesn't change, and response becomes slower. Okay, these two are the essential results with derivative action. And some idea about this derivative. For constant non-zero error, derivative mode does not give any output. Otherwise, so if you suddenly change the error and again keep the error constant, for such a thing, this derivative mode won't work. Otherwise, for step change in error and error remaining constant, this derivative mode won't work. So otherwise, most of the time you'll change the set point, or the disturbance changes suddenly and remains at the same level. So for such an kind of inputs, this derivative mode is not suitable. So otherwise, derivative mode cannot be used alone, because most of the time we'll have change in error and persisting error. So for the persisting non-changing error, this D action won't give any output, because so dE by dt, E remaining constant. So dE by dt is not. Tell me, Mathis.
Sir, if D action reduces the order of the system, then
not,
why
it's not reducing the order. It is changing. Doesn't change the order.
Okay, sir. அப்படி இருந்தா கூட speed of response வந்து ஏன் சார் decrease ஆகுது? Increase தான் சார் ஆகும், improve தான் சார் ஆகும்.
சரி, speed of response ஏன் குறையுதுன்னா, இந்த இதெல்லாம் this is the final form equation. So final response. This equation is a final response. என்ன பண்ணுவோம், in comparison with the first order, how it is comparing, no? So first order system will be having kp by tau ps plus 1, right? No?
Yes, sir.
So it is now turning to tau p is turning to now tau p plus kp kc tau d. Say these are all non-zero values, and say even though any fraction, definitely this tau p is going to be increased. Tau p will be increasing. Tau p increase such an now the response will be slower. You know, how do you say it, tau p increase is going to slow the response? Let us go back. The first order system படிச்சீங்களா? First order system, say this also like first order system or output எப்படி இருக்கும்? kp by this is the thing. So kp by tau ps plus 1 for what is the response? Kp dash into, see for this the response is 1 minus this form. So இதோட the first order analysis la படிச்சோம்லப்பா, tau p lesser the tau p, faster the response. This already we have. Maybe I can even give you the response curve. ஏற்கனவே டிஸ்கஸ் பண்ணியாச்சுப்பா. அதாவது டைம் கான்ஸ்டன்ட் ஜாஸ்தி ஆச்சுன்னா ரெஸ்பான்ஸ் ஸ்லோ ஆகும். See for example here, no, with increasing time constant, the response is we have a slow response. See this can be easily understood, no? See thermometer ஒரு பெரிய thermometer இருக்கு, so a very small thermometer, this which thermometer will be responding faster, or is the thermometer with a thin bulb, no, which will respond faster, because it has a lesser capacity, so it can quickly take the temperature of the surrounding, so it will respond faster. So always with derivative action, the response is becoming slower. There is a output.
Sir, then why do we need to implement D action, sir?
Yeah, still D is having a lot of good role to play. So that and all we can only see with this closed loop ஒரு பெரிய ஒரு சிமுலிங்ல போட்டு காமிக்கிறது ஈஸிப்பா. We know this with I form, integral controller. I will quickly give you the result and come back to the discussion. எங்க இருக்குன்னா ஒரு நிமிஷம் பார்க்கலாம். I will get you the result alone, and so I'll take this book. கொஞ்சம் ஸ்லோவா இருக்கணும் sometimes தேவை இருக்குப்பா. Yeah, question is why if the controller is, if the response is slower, why should we use it? Nice question. Sometimes ஃபாஸ்டா இருக்கிறதும் தேவையில்லை, சில இடத்துல ஸ்லோவாகவும் இருக்கு தேவை இருக்கு. ஒரு நிமிஷம், I'm looking for the corresponding. Okay, otherwise it is there in my book. Directly I will show you. Yeah, raise ஒரு நிமிஷம் வந்துருச்சு நினைக்கிறேன். Yeah, right. See this graph, no? With no control, actually the output will settle at output will go in this trend. Okay. Say this is for actually what is called as a load change. So response of a control system, feedback control system with various modes of control. See the one corresponds to the response of the system for what is called as changes in the load. And with two, what is called as a proportional action, we see there is an offset. So offset is now compared with the expectation that it should still remain at the value of 0. In spite of any change, that should be the system should follow the change. And here we are now changing the load. In spite of any changes in the load, the system should remain at the initial steady state. Initial steady state is simply the 0 horizontal. This is the 0 level. Whereas with no control, the system is stabilizing at another value. That is what is a first order system. Now we are changing the input and it is now settling at a new value. That is a first order system. With P control, actually with P control, there is a offset still remaining. And with I control, so we could eliminate the offset, or the P plus I is eliminating offset. Even with I itself, we can eliminate the offset, but P is sometimes useful to make the response faster. Okay, that's what is the expectation of P control. And with PID control, so what is happening? Say the 3 is having some oscillation. No? What is it? This is from proportional plus integral action. Whereas with derivative, by the addition of derivative, the oscillations are now suppressed. Otherwise, we could make the system to stabilize at a much lower time. Matheswaran, புரியுதா பாப்போம்?
சார் நீங்க ஆனா ரெஸ்பான்ஸ் வந்து டிக்ரீஸ் பண்ண சொன்னீங்க, பட் ஆனா இது இன்க்ரீஸ் தானே சார்? லெஸ் டைம் கான்ஸ்டன்ட்ல வந்து செட் பாயிண்ட் ரீச் ஆச்சுன்னா அது வந்து ஸ்பீட் ஆஃப் தி ரெஸ்பான்ஸ் இன்க்ரீஸ் தானே சார் பண்ணிருக்கு PID பை டிக்ரீசிங் தி ஓவர்ஷூட்.
யா, ஓவர்ஷூட்டை குறைச்சிருக்கு.
So response automatically increase தானே சார் ஆயிருக்கு?
Yeah, response is faster because of the other modes. PI are there already, no? So now only D is added, but D add பண்ணதுனால PI is better now. Say this curve 3 corresponds to PI.
Yes,
so with the curve 1 corresponds to no control. This two corresponds to P control. 3 போட்டதுனால என்ன ஆகுது? Offset is eliminated. That is PI control is eliminating offset, but still having a lot of oscillations. The oscillations குறைக்கிறதுக்கு this D is doing that role. But order மாற போறதில்ல. Oscillations are getting reduced. Okay, இப்போ கன்வின்ஸ் ஆகலைன்னா இன்னும் 2-3 கிளாஸ்ல கன்வின்ஸ் ஆகும். பிகாஸ் we'll see that with Quick at that equations I cannot easily say. But with this closed loop, you will be in a position to understand. Okay, Pakla. Madheswaran, இப்போதைக்கு convince ஆடலாம் இந்த 2-3 கிளாஸ்ல உங்க ப்ராப்ளம் क्वेश्चन தெளிவாயிடும். Okay, we'll now go to I will I'll give you a Simulink loop. I will try to explain these ideas. And there is topic is about because of the controller, whether the system is still in the steady state or whether it is going to any unstable behavior. That I am going to explain. Okay, this and all we have seen in the last class itself. I am going to give you the another loop. Maybe close automatically or so. Peak controller. You have to close right. Fine. இதெல்லாம் க்ளோஸ் பண்ணிடுறேன். தேவையில்லாதெல்லாம் டிஸ்ட்ராக்ட் பண்ண வேண்டாம். ஓகே, ஒரு நிமிஷம். Okay, we have a closed loop. The measurement is also having a transfer function, which means measurement is also having some lag, or is a first order system. So measurement, fast measurement, now you can take it as simply a gain of 1, or is it is zero order system. Gain is a zero order system, or is proportional control is a zero order system. Zero order means fast, immediate response. See what is there in the loop? We have there is two first order system, or is a system is there are two first order system in series, and measurement is also considered to be a first order system. So let us see the response of the system for various values of controller gain. And இது வேணா நீங்கள் கூட வரைஞ்சு பார்த்துக்கலாம், பட் Simulink is now slower இல்லையா? The latest versions of MATLAB is at least the Simulink is very slower because of the file size is bigger. I don't know. Okay, we have two first order system. Always it is a second order system. Simply the process is a second order system. The measurement is also having a first order. And let us see the response of this loop for a set point change of 1. And even you can take the step time at 0 itself. Always at a time of 0, set point is changing from 0 to 1. So you can see the response by running the simulation. So maybe I can even connect this. I will take one more. Let us see the response with. We can compare the set point and the output. So for that we can have a multiplexer. So we are taking two input and giving it to the scope. Okay, so there are we are going to compare this thing. Okay, the input is changing to 0 to 1 at time of 0, and output. So you can definitely expect this is a second order system, and even measurement is also having a order. So the closed loop will be a third order system. How do we say it is third order? Because in the denominator we'll be having 1 plus GP, GM also will be there. So GP is already a second order, GM is a first order, so we'll be having a third order. Sorry, GP is a second order and GM is first order, so GP into GM will be having a third order system. So the response, you can see the response is shown in the blue color in the output window. So response is settling at a value of somewhere around 0.5. So otherwise your expectation is always we are changing the set point to 1, but output is settling at a value of only 0.5. So what we'll do, we'll change the gain value. So gain adjust pannalam. So what is the need for raising the gain? We want to eliminate the offset. Yeah. So to eliminate the offset, what we can do, we can simply keep on raise the value of Kc with only P controller available. Otherwise, if we have a I controller, I controller will eliminate offset. It will automatically eliminate offset. You can see that this also. So how do we say it's how to make this as a P I controller? We can have a integral one போட்டுக்கலாம். So how to have an integral, and we can have a integrator one போட்டீங்கன்னா. So now integrator is having value of 1 by tau is. This tau is also 1. So Kc is also equal to 1. So you can see the output. So output is settling at a value of 1. We don't see whether it is settling because the time is not sufficient. Let us raise it to some 100 and run it again. So you can see that the output is settling at a value of 1. Otherwise, there is a set point. Set point order value output is set light. So otherwise, we could eliminate the offset by having the integral control. How do we say this integral control? This Kc by tau is. This tau I and Kc are assumed to be having a value of 1. Otherwise, you can change them by changing this value here. Class follow பண்ணிக்கலாம்ப்பா. Now, the original thing is instead of integral control, we'll try to reduce reduce offset by with the proportional action alone. So for that, I'll again see the response. Then only you can compare. So the input is changed to 1, output is settling at a value of 0.5. So output to reduce the offset, we can keep on raise the value of gain. So the gain, the offset is now getting reduced. It is somewhere around some 0.65, 1 minus 0.65, or is 0.35 we have the offset. Okay, offset குறைக்கிறதுக்காக நீங்க gain மாத்திட்டே போலாம். Suppose you are changing the gain to some value of 8. So what happens is the oscillations are coming out, and still the output is not settling at the expected input, expected change. Instead of settling at 1, it is settling at a value of somewhere around 0.8. Of course, we have a lot of oscillations. 8 பேல நம்ம இப்போதைக்கு 10 போட்டா என்ன ஆகும்? 10. We are seeing a typical case. It is not general case. At a value of Kc of 10, any system will be unstable. For this problem, this is we are seeing. See, we can see the oscillations are keep on there, but still oscillations, of course, they are going to reduce. Say, suppose a value of 11. What is happening? So you can see you have a closed loop with increasing oscillations. Otherwise, your from the originally stable system is now becoming an unstable system. Originally stable, otherwise initially at least set point 1 கொடுத்தீங்கன்னா with no controller, the output is also at least settling at a value of 1. Otherwise, if you don't have this measurement and controller, this will settle at a value of 1. Whereas with a controller, we are making the system to be worse. Worse. It is turning to worse situation because instead of settling at a value of 1, it is keep on increasing, and the values are going around 400, 500. Otherwise, the system is going to unstable behavior. Instability is introduced because of the controller. So till what value of system, what value of Kc the system is stable, and how to find, sir. Sorry. And still, till what value of Kc the system will be stable, and how to find a system is a closed loop system is stable. There is a topic of discussion in the coming topic. How to find a system is stable. How to find a closed loop system is stable. Of course, simulating you can run the simulation and see the response. Whereas it should be mathematically provable. No? So for that, there are methods available to say about the stability. So before that, we'll see about what is called as the pole zero representation of a system. Okay, இதுவரைக்கும் புரிஞ்சதாப்பா? To quickly summarize, say we have a closed loop system. The closed loop is coming because of a measurement and controller combinations. And with peak controller, there is always offset there in the system. With I control action, we can eliminate the offset, but it is going to increase the order of the system. With D control, we can slow the response of the system. That is also helpful. That we can understand that the effect of D control in the coming topics. And if you try to eliminate the offset, say by the simplest controller action P control with keep on increasing the gain, at some conditions you see that the system is turning to unstable condition. So how to find whether how to check the system stability, or is on what basis we can say about the system is stable or unstable. Of course, if you can plot the response, you can see the response is definitely showing that it is a unstable system. But can we say simply based on the this transfer function of the closed loop itself? That is a topic of coming discussion. So before that, we are going to see about a new topic, what is called as pole zero representation. Okay. So that is a topic. Say any closed loop, say OS by XS refers to output by input in terms of Laplace transform. So that is what is called as a GS. There is a transfer function of the system, and we can write this polynomial in terms of these poles and zeros. So poles are nothing but the roots of the denominator, and zeros are nothing but the roots of the numerator. Okay. Otherwise, what we are writing, we are writing this polynomial. So this polynomial, how do you get? If you simply expand these groups in the denominator, and you will be getting this polynomial. And this polynomial, you can write this in terms of this polynomial roots. Say, given this second order polynomial, you can easily get the roots. Third order, you have to again work out. Fourth order, suppose you are given with a computer, you can easily get these roots. Okay, so we can get the roots of assume you are given with the roots of the this polynomial. We know the transfer function of this form, like say s minus z, which is in the zeros form, and s minus p's. These are all what is called as poles. And based on the location of the poles and zeros, we can say about the stability of the system. That is a topic. Okay. Say suppose the poles are simply, I will represent these. Yeah, 1 minute. So the poles are the values of S that makes the denominator the transfer function to 0. So what is the meaning of a pole? So at the value of pole, so if you take the roots of this polynomial, the denominator is 0. Yeah. So raise say the poles are the values that makes the denominator of the transfer function to 0. Likewise, zeros make the transfer function, the roots of the numerator of the transfer function to 0. Okay, these are all understandable. So here for this polynomial, so this poles are at -1, -3, and -4. Or simply this or if you write it to a form like s minus p, s minus p1, s minus p2, s minus p3. So p is equal to -1, -3, -4. Likewise, s minus z1, s minus z2. So z1 equal to -1, z2 equal to -2. So we can locate these poles and zeros. Before that, of course, any physically realizable system is the output order and our input order. That is the order of the this output terms. So there is d square y by dz, sorry, d square y by dt plus dz, dy by dt plus some constant equal to dxy dt எல்லாம் போடுவீங்க இல்லையா? So the any physically realizable system, at least at the most the numerator and denominator and numerator should have the so the physical okay, the denominator coefficient should be always denominator should be always of higher order, or at the most it can be of equal order than as that of the numerator, whereas this one is unrealizable system. Or is input output தான் வந்து should have the higher order. Okay, this is what is called as unrealizable system. இதுக்கான example I could not give. Okay, yeah, see this about the representation of these poles and zeros. So this kind of response we'll be getting with poles of what is it? Okay, how to represent the poles and zeros based on the roots. Say this anything in the real axis, these are all real numbers, and for complex number you can represent them in the imaginary axis. Say you know this -2, -1, these are all the real numbers. Suppose you have -1 plus or minus 2j, so this is represented by this way. Okay, so this is a complex number, so whereas this is a real number. So whereas -1 plus or minus 2j is represented by this way. Okay, so we already know this S can be a complex number. So for a second order system with underdamped characteristic, we have what is it, a complex number as the roots. And again we are going back. So because of the complex number coming in, we will be getting kind of oscillations in the response. Otherwise the complex number if you take the time domain, it will be coming in terms of sine and cos. Otherwise sine function you will be getting. The nature of the sine function is giving you you will be getting oscillations in the response. Say the roots what is it, the pole values which are all having negative and real parts will be falling in these regions, otherwise to the left of the imaginary axis, whereas the poles with positive real parts will be coming in this right side of the imaginary axis, or is right to the right of the imaginary axis. And if you plot this response, the response will be what is it, a decaying output for what is it, a real number. So the response is nothing but the exponential decay, no? So for for S1 it is plotted here. This one is plotted here, so it's starting at a value of 1 and it is keep on decreasing and it will settle at a value of 0. So whereas with what is it, with a complex number root, with complex root we'll be having oscillations, but again oscillations are decaying. It's decaying because of we have negative real part. If the root is having only imaginary part, we'll be having undecaying oscillations, what is called as the zeta equal to 0 in the case of your second order system. Okay, so we'll be having undecaying oscillations. If you have a system with what is it, the positive real part, or with a system with only a positive real number. So for with positive real number, we'll be having a growing response. See, the response is keep on increasing. So what is called as ever growing response. If you have a positive real part or a positive number. So for with the positive number, we won't have any oscillations, positive real number. Whereas with positive, or with a complex number with positive real part, we'll be getting this kind of response. What is it? We have a response with growing oscillations. Otherwise, you can simply based on the roots of a transfer function, we can say whether the system is whether the system will be whether the response will be growing or decaying. So we normally want a response to say settle at its initial conditions. Otherwise, decaying response. That is what is the expectation. Otherwise, we expect the roots to lie in the negative real part. If the roots are lying in the positive real part, we will be having a growing oscillations or a growing number. So otherwise, the summary is now given like this. So based on the roots of the characteristic equation, say in the case of a second order system, we'll be having a characteristic equation as s square plus 2 tau, tau square s square plus 2 tau zeta s plus 1. Yeah, that is a response. That is a characteristic equation. Based on the roots of that characteristic equation itself, we can say whether the system will be stable. How do you say we can get the this tau and zeta, and if the zeta is say what is it? All this thing we expect to be a positive quantity. If they are turning to be a negative thing, we'll be having this kind of trend. Otherwise, this zeta, not zeta. Otherwise, if you have these roots as a plus ib, this a should be a negative quantity. If it is A is negative, then we'll be having everything. The response is in this negative side, or is the side we'll be having the response will be in this region, and we won't have any stability problem, always unstable conditions. Whereas the roots are having positive real parts, then we'll be having this kind of response. Always we'll be having growing oscillations. So this concept is actually used to check whether the system will be stable or unstable. We can simply get the characteristic equation of the system, and based on the roots of this characteristic equation, we can say about the stability of the system. Okay, we'll discuss about this aspect in the coming class. We'll go back to the MATLAB simulation on port. Even I said about what is it? Load change. For load change, we didn't study about the load change, but I have said about this. You can take it for granted. How to study for load change, that we can see now. So I am taking this Simulink again. So let us take this everything to be 1. So simply we have a closed loop with a measurement transfer function of 1. And what we are going to do, we are going to have a load system with load change. Can flip the block. How to flip block, counterclockwise. Right. Rotate block will be there. So we can rotate the block. No, we can rotate it. We should be rotate it. That can score 1 minute. I need to connect the load. I will rotate. Yeah, actually there is another easiest way available. Okay, 1 minute. No, one more rotation will be giving. In what way? Counterclockwise. Flip horizontal will be there. No? 1 minute. So I need to connect a load which is having a transfer function like this. So let us see the response with a step change in load. So load is there. இதை கனெக்ட் பண்ண போறோம். அதுக்கு முன்னால இதை கொஞ்சம் மாத்திக்கணும். Of course, you can play with the signs and you can change the thing as well. அது மறந்துட்டேன் இப்போதைக்கு. Let me try. இது பண்ணா என்ன ஆகும் பார்க்கலாம். Fine. So instead of plus minus are changed, I can change the signs alone. Even this also will make it as 1. Service, we have a first order system like this. So we have a first order. Okay, already it was. Okay, you can connect this. So we have a first order system, and we have we can connect. Okay, no problem. Let it be here. Okay, this is we are changing the load. Set point instead of set point is simply not changed. Otherwise, initial value, final value, everything made it as 0. Class follow பண்ணிக்கலாம்ப்பா because I'm நடுவுல எதுவும் கேட்கவே இல்லை நான் உங்ககிட்ட. Okay, still about 55 people are available. Another about 10 minutes, no? So that we'll see the response of this thing. Yeah, no problem. Initial time is 0. Sorry, step time is 0 and initial value is 0 and final value is 1. So we have what we have? We have a system with load change. Step change here we don't change anything. No, initially it is 0, finally it is also 0. That means the set point is not changed, and load is to be changed from 0 to 1 in a time of 0 itself, and we are going to see the response for a time of say 100 seconds. It's 100 time units, not seconds or minutes. 100 time units. We can run this. There is a loop. Set point. Okay, 1 minute. We'll have a simple system with gain of 1 and time also let us reduce so that we can see. So what we have a first order system, and what is the set point change? Set point is 0 change to 0 to 1, and so set point is remaining. So not set point, it is load variable is introduced. Say load variable, and say initially there is some flow, and suddenly the flow is changing, and we in spite of any change, you should see the output should remain at the initial level of 0. Say initially the system is remaining at a value of 0, and there is a disturbance entering at a value of 1. See now we see actually yes, sorry, the load can also have a positive. It can have a positive, no? It can affect in a positive way. So that's what is the thing we have derived for our level system. So let us see for a positive affecting. The load is affecting in a positive way. So we see this is the change, or is change, disturbance is changed. There is a persistent disturbance at a value of 1, whereas your output is initially it was at 0. Because of this persisting disturbance, you see the output is settling at a value of say somewhere around 0.5. But what is a good controller? And the controller should reject any disturbance. So otherwise we should eliminate the offset. So what is why it is offset? Otherwise instead of settling at a value of 0, it is settling at a value of 0.5. So let us try to increase that gain. So with increased gain, now we see the offset is somewhere around some 0.18. ரைஸ் பண்ணிட்டே போனீங்கன்னா you can see the offset will be reaching a value of 0. Sometime it may also lead to unstable condition. Okay, that's what we have seen in the first aspect. Okay, otherwise we have studied the closed loop response for changes in the load, what is called as disturbance rejection problem. Say there is a disturbance entering and the closed loop should work on to reject the disturbance. That is what is called as a disturbance rejection. Otherwise it is called as a regulator problem. So of course you can see the combined response also by changing the set point as well as changing the load. So if you change the set point to 1 as well. So otherwise load is changed to 1, set point is changed to. So what is the expectation? So we should, the system should settle at a value of 1. Instead of that, it is simply settling at some other value. Okay. Okay, this and all we will discuss in the coming class. Otherwise, we are going to just introduce about the concept of stability. Not the concept of stability, otherwise how the unstable conditions are coming out because of the controller action. See, sometimes if we keep on increase the gain, sometimes instead of the system becoming stable, it is leading to unstable conditions. And to check the stability, we can simply analyze the roots of the characteristic equation, and based on the location of the roots, or is what is called as the poles and zeros, we can say about the stability of the system. And for a stable system, the roots should lie in the negative real axis. They should be in the negative to the left of the imaginary axis. Okay, to the left of the imaginary axis. That is a topic. Okay, this idea and all we'll explore in the coming class, and in that, in the coming class, we'll say about a new topic what is called as route stability. That is the easiest aspect of this control system. The answering, if you want to answer this control system question, if there is any route stability question based on route stability, you can easily take up that question. So on the topic we'll finish this portion for test. What is it? Test 2. So test 2 what sort of questions will be there? Kind of proofing question. We'll be asking you to prove certain things and to find the response from the P controller, I controller. So the சின்ன questions தான் கேட்க முடியும். Okay, I will also collect some questions for you to work on. What is called as some problem sheet I will give. Okay, this will and say the coming Wednesday class is very important class. Don't miss that class. So adalanda nare questions